count the number of solutions to this modular arithmetic equation. This one right here, x to the 6 is congruent to 1 modulo 19. And I'm going to start by comparing it to something that we can do fairly quickly. Let's consider x to the 6 is congruent to 1 mod 8. Okay, and again, y'all, I just wanted to show you you might be tempted to say just 6 and on to the next problem, but there's some work required here to actually count the solutions, not actually find them, but count them. Now, but the simpler case right here, you can actually write down the answers here. X would have to be equal to all the odd numbers up to 8. So we would have x has to equal to 1, 3, 5, and 7. And you can check those by inspection if you want to. And there's a result, a more abstract result or fundamental result that shows you why that's true. But so there's 4 solutions here, 4 of them. Now, a lot of you guys, there's a very familiar result, I guess, in a first year number theory course or even in abstract algebra. I actually saw it in Durbin's abstract algebra book. But a squared, if a is any odd integer, if a is odd, let me just write this down. A squared is congruent to 1 modulo 8. And that's a fairly easy proof just by writing down a is equal to 2k plus 1. Okay, it's not hard to see that. Okay, and again, so this is true for a odd. A is odd. Okay, a is odd, and the only odd numbers up to 8 are 1, 3, 5, and 7. So there's 4 solutions, and this is, again, you can prove this on your own, or you can just check by inspection. Well, it's tougher to, it's kind of hard to do the arithmetic, but notice that x to the 6th is the same thing as x cubed squared, right? So it is a square, albeit one with larger numbers, but x to the 6th is x cubed squared, and any square is congruent to 1 mod 8, provided that number is an odd number. Okay, so that's the answer to this question. Now let's start looking at the solutions, how we would count the solutions of this modulo 19 version of things. Okay, so again, degree 6, we have a degree 6 up here, but only 4 solutions. Okay, now let's count the number of solutions to this guy right here. X to the 6 is congruent to 1 mod 19. Okay, now a good start almost invariably is to see if we can factor, get this to appear in some known factorization. Now, just another way to write this modular arithmetic statement or this congruence, you can write it as x to the 6 minus 1 is congruent to 0. Okay, and of course we're talking mod 19. This and this, just like regular equality when you're dealing with congruences. For many, that's why congruences are so popular. For the most part, it functions and behaves and acts like equality. All right. So now this algebra, this is a telescoping sort of situation right down here. X to the 18th minus 1 has our object of interest, x to the 6 minus 1, as a factor. Okay. Now there's something that comes in quite handy called the Euler Totient function. And this is always true. A raised to the alpha, or that's not alpha, that's, what is it? Phi? Yeah, phi of n. A raised to the phi of n is congruent to 1 mod n whenever a and n are relatively prime. So in particular, we get a, and let me write this, a, and y'all might have a hard time making this phi, to the phi. Okay, there's my phi, folks, my best rendition of a phi. And we're going to call it P. Okay, P stands for prime. Okay, a to the phi of P is always going to be congruent to 1 because everything less than P is relatively prime to P, basically. Okay, now off to the side here, let me write something that's a little clearer. And you can almost define prime numbers this way. Phi at P phi at p is always equal to p minus 1. And y'all, phi is a counting function. It counts the number of elements less than the input argument that are relatively prime. Well, a prime number being defined the way it is has exactly p minus 1 elements that are relatively prime to it. Otherwise, it wouldn't be a prime number. So if you define the phi function first as the number of elements that are relatively prime to the input argument that are less than the input argument, okay? If you define that first, then you could define a prime number this way, actually. And I think some current modern number theory textbooks do it that way, okay? But in this particular case, this works out nicely for us since 19 is prime, right? So a special case of this Euler Totient function is we get x to the 18th is congruent to 1 mod 19 for x equal 1, 2, 3, all the way to 18. Now notice zero's not in here. Zero's not in here because the GCD of 0 and 19, excuse me, would just be 19, right? That's a special property. Everything's a divisor of 19, right? So that's why we leave 0 out. And it's a good thing because that means there are 18 solutions to this guy. And this is much like how it is in regular polynomial stuff. That you can have no more solutions than the degree of the polynomial. In this case, it's the same here for number theory, okay? So what we know is that x to the 18th minus 1 has exactly 18 solutions, right? So you see from here, we're essentially done with the proof because there's exactly 18 solutions. The object we're interested in can have no more than 6 solutions, and this one can have no more than 12. So since there are 18, this one has to have exactly 6 solutions, and that's the answer to our question. 6. Let me just put equals 6 there since I'm not able to write, folks. Okay, so that's 6. And over here, of course, this is 12, which is not important. But the solutions have to be distributed this way because we know from the Euler Phi function that x to the 18th minus 1 has 18 solutions, right? So they got to go somewhere. All of these, this can have no more than 6, this can have no more than 12. So this is the only possible way to distribute the zeros, if you want to call them that, okay? So the answer to the question, a little anticlimactic, but the answer to the question is 6. Okay, and I'll try to spell 6 without the mouse wiggling here. And y'all, again, it's not always, the reason why I showed the example, I know I'm belaboring this point, this is x to the 6th degree 6, but there's only 4 solutions, right? So it's not always, and it's like x cubed equals negative, x cubed is equal to 1. Real numbers only has one real solution, namely 1, right? So even though its degree is 3. Same thing right here, but this one did happen to have 6 solutions, which corresponds to the degree of the modular arithmetic expression. All right. Okay. Thanks for viewing.